is one of the most popular and commonly accepted biometric hallmarks that has been used since the ancient times, right? So for verifying different entities related to human beings. The examples are the documents of forms and bank checks and various other things. So signature is a person's name written in a distinctive way as a form of identification in authorizing a check or document or concluding a letter. Now, signature forgery refers to the act of falsely replicating the signature by of another person, right? And signature forgery is done in order to commit frauds, deceive others, and alter the data. And one common example of signature forgery is check writing, right? The bank check writing. Therefore, signature verification is a critical task, and many efforts have been made to remove the uncertainty involved in the manual authentication procedure, right, which makes signature verification an important research line of field in the machine learning and pattern recognition. Unlike other verification problems, it needs to model minute but critical details, right, between the genuine and the forged signature, because a skilled falsification might only differ from a real signature by some specific kind of deformation. Now, there are, predominantly two types of signature verification that is actually there right now. The first one is the online signature verification, that is capturing the signature by the use of writing pads together with a stylus, right, which can mainly record a sequence of coordinates of the electronic pen tip while signing. Apart from writing coordinates, the signature of the signature, so these devices are also capable of fetching the writing speed, pressure, and additional informations, right? So which are used in the online verification process. On the other hand, the offline signature is a bit different and is usually captured by a scanner, right, or any other imaging devices, which basically produces two-dimensional signature images. Online verification systems generally perform better than their offline counterpart because there are other data also available, right? The complementary information such as the stroke order, right? The speed and pressure, all those things, right? But this improvement in performance for online verification process comes at a cost, right? Because it requires special hardware for recording the trajectory, the speed, and actually it reduces the real application scenarios also, right? Because not everywhere you can actually utilize that. And for example, there are many cases, right, where authenticating offline signature is the only option, right? So for example, if we want to do the check transaction, right, or document verification, we cannot go for the online, right? So still offline verification is very important and prevalent, and it is very important to look at it, right? So let me see if there are any. So keep on posting your questions, right? I'll be periodically checking the chats, right? And I'll try to answer that on the fly itself, right? All right. So now, how to solve this particular problem using a standard CNN, right? The convolutional neural network, right? So in case of standard CNN classification, what happens is the input image is fed into a series of layers, right? And finally, at the output, we generate a probability distribution. So for example, let's say we are talking about 10 people, right? So we are trying to classify a signature to detect which person it belongs to. And let's assume, there are 10 people, in the bank's client base, right? So for every input signature, we generate 10 probabilities, right? Indicating the probability of the signature belonging to each of those 10 classes, right? And what we can do is, if the probability for the corresponding user is greater than some threshold, right? We can define some sort of threshold, and we can say that if the probability for that particular for that corresponding user is greater than this threshold, then it is a authentic signature. Otherwise, it is not, right? So that way we can solve it, right? Now, there are two main problems for this, right? So the first one is to train such a system, we first require a lot of different images, right, of each of those 10 people, right, in the organization, which might not be feasible, right? So for example, just imagine if you are having thousands of employees in the organization, right? So it is not a feasible way to collect data. And the second point is, what if a new person joins or leave the organization? So you need to take the pain of collecting data again and retrain the entire model again. And this is practically not possible for large organization where the the recruitment and the attrition, right? I mean, it is happening almost every week. I mean, if not daily, right? In the financial institutions like banks, we neither have enough data for each class, right? Well, class means like, I mean, for each people, and the total number of classes is also huge, right? And that is the client base itself, right? And it is dynamically changing a lot, right? So there's the cost of data collection, and also the periodical retraining is quite high. All right, and that's why few-shot learning is here to rescue, right? So what exactly it is this few-shot learning, right? That is, we require only few training examples for each class, right? So typically, if you look at these banks, right? I mean, while you create an account, right? How many signatures you do? Probably 6, 7, 8, max 10, right? That is the number of signatures you're actually doing on the documents while you create an account, right? And that is exactly what few-shot learning thrives upon, right? So it requires few training examples for each class. And instead of directly classifying an input image to one of those 10 people in the organization or the bank that we talked about, right? This network instead takes an extra reference image of that particular person, right? Which is the ground truth, right, for that organization, right? That is one of those signatures from those 6 or 8 signatures while I created an account, or when I go for a change in the sign, right? So those are the things that gets captured, right, in the bank database, right? And that is actually taken as an input, and it will produce a similarity score denoting the chances that the two input images or the signatures belong to the same person, right? Now, typically, this similarity score is squished between 0 to 1, and using a sigmoid function to where 0 denotes no similarity, 1 denotes full similarity, right? And any number between 0 and 1 is interpreted accordingly, right? So we shall use Siamese network, which is one of such example of few-shot learning, right? So how does this solve the two problems of the CNN classification that we talked about, right? So in the demo, we'll see that to train this network, you do not require too many people, right? Too many people's signature, and only few are enough to build a good model, right? But the biggest advantage is, let's assume that we have a new customer who gets onboarded in the bank, right? And now in order for the network to detect his signature, we only require a single image of his signature, and we can just use that for identifying whether the signature is forged or the genuine, right? We don't have to retrain the model, right? And using this reference image, the network will calculate the similarity for any other new instances that is presented to it, right? Yeah, well, okay. So I don't see any questions, so I'll move forward. Well, so what does this Siamese network, Siamese architecture actually looks like, right? So it is a class of neural network architecture that contain two or more identical subnetworks, right? Identical here means they have the same configuration with the same parameters and same weights. Now, parameter updating is mirrored across both the subnetworks, right? As you can see in the image, and it is used to find the similarity of the inputs by comparing its feature vectors, right? So both those networks in the top and the bottom, right? So they actually transform the input images into a feature space and the feature vector, right? And then the similarity score or the dissimilarity score, the way we want to make it, right? That is actually calculated. So in this regard, a signature verification can be efficiently modeled by Siamese network, right? Which consists of twin convolution network, the name it suggests, right? So that is the Siamese itself. So now there is a very important difference there, right, with the traditional CNN and the Siamese network, right, which actually lies in the loss function itself, right? So now, if you see, for the training purpose, right, we use pair of images as a single training example, right? But for CNN, we are using individual images as the training examples, right? So that is the difference, right? And because of that, cross entropy cannot be used here, right? And that's why we use contrapositive loss. And it is a popular loss function used highly nowadays. And it is a distance-based loss as opposed to more the conventional error prediction losses. And this loss is used to learn the embeddings, right? In which two similar points have a low Euclidean distance and two dissimilar points will have a large Euclidean distance. And from the equation that is there, you will see that it is very, very similar to the cross entropy, right? Rather, instead of the probability component, we actually have the distance component, right? Which is the Euclidean distance. And there is a m variable, which is the margin, right? Typically, it is set to 1 or 2 value, right? To kind of constrain the distance measure, right? So that's all the difference between the CNN and the CMS network. So how to build such models, right? So we have used SageMaker, right, as a platform to train and deploy the model, right? And we used PyTorch for building the model, right? So SageMaker gives you the pre-built Docker images, which has all the requirements installed regarding the PyTorch and all the PyTorch related dependencies also, right? And we can easily spawn such instance and we can train on that particular instance, right? So enough of talking, right? So let's see how to build such model actually using some real data, right? And using some real code, right? So we have used a BigSig 260 dataset, right, which contains labeled images of Hindi and Bengali signatures. It is an open source dataset. So the links to all the code, the dataset, and the relevant materials, everything I have put it in the reference section. And I shall push this presentation also to GitHub after this talk for your reference. So first, we define and import, define all the imports and the helper functions to plot the loss function or to visualize the images, all those things, right? Then we split the dataset into 3 parts, right? The training, the validation, and the test. And each of those having 3,000 signature image pairs, right? But so just try to understand, it is a signature image, pair, right? So it is not the count of individual signatures from individual people, right? Because we do this quadratic, combinations, right? And that's why it actually creates those many number of training examples. That's how it is. So then we define the constants and the hyperparameters, and you can see that the train, validation, and test set contains disjoint sets. Like disjoint set means disjoint users, right? So each containing images from only 3 users. And I've just kept it like this just for the demo purpose. We can keep on increasing that, and we can try it out also, right? And then we define the constants and the we define the custom dataset class, and here also we define a way to kind of tag the pairs, right? So that is whether it is 0 or 1, right? Here we actually mean 0 means genuine, 1 means fraud. So it is, you can think like, it is a dissimilarity score in where we are actually heading towards, right? So 0 is genuine, 1 means fraud. So dissimilarity score we are actually trying to model. And then we load the dataset in the PyTorch data loader so that we can iterate over it and we can train it. So let's visualize few pairs, right? So what those pairs look like, right? So as you can see, the first 2 are forced because the actual values are 1, because we actually mapped it to a dissimilarity space, right? And the last one, you will see that it is 0, and that's why it is genuine, right? Okay, so let me see. How do you ensure at test time when a genuine user signature is little deviating from what we have in training? Okay, so while training and so as I'm taking you through the code, right? So training and testing, they have they can have completely different set of images, right? Like different set of people altogether, right? So you can think that based on your and my signatures, the model is trained, right? And somebody else, let's say some guy named Varun comes, right, to the bank, and he actually registers himself in the bank with some sample signatures, which actually comes via the bank form itself, right? And those images can be used as the ground truth, and they can be part of one of those pairs, right? And then the check comes from Barun, right? So that signature will become the other part of the pair, right? And then the prediction will happen, right? And you can understand, right? So Barun's data was never used for the training purpose, right? And still it can be used, right? So that is the beauty of that cross entropy. Sorry, the contrapositive loss, right? That actually models this thing irrespective of the writers, right? So that it is a writer independent system that we're building, right? Will image augmentation help here? Definitely, image augmentation will help, and that is what we typically do also for one-shot and few-shot learning to increase the number of training examples. That's right. Yeah. So that's why. So while we actually build a deep neural network, right? So the aligning the signatures might not be required, and at the same time, you are also right at one perspective. That is, what we can do is we can have different sort of rotation of the input pair itself while doing the prediction, right? And then we can take an average of the scores that we are getting, right? So to kind of reduce any such noises that can actually arise due to alignment. All right, so how can we use the attention mechanism in the network so that interpretability will be done, so that based upon which part of the image it is predicted and real? So yeah, so there has been a great deal of research done on the attention mechanism. So, but as it is for the stock is for the general purpose. That's why I kept it very simple so that people can appreciate why we are requiring the CMS network. But yeah, that is right. Attention mechanism that can be utilized on top of it. So we can actually definitely probably sync back later offline, and we can discuss more about it. All right. So this is the network that we are going to implement, and it is from a paper called SIGNET, and the link to the paper is also part of the reference that you can find. Now the code for doing that is here, right? So I'll not go in detail. So I'll just explain the first layer itself, which is actually the first convolution layer filters the input signature image with 96 kernels, and each having size 11 and with a stride of 1 pixel, and then eventually we have the second and the third and the fourth layers subsequently, and in the last layer if you see that there are 128 neurons. So eventually both the images are going to be would be mapped to a 128 length feature, right? In that dimension it will be mapped to. Now, if you see the code, it is only a single model, right? So, but in CMS network we talked about 2 models, right? So where is the other one, right? So since we talked that both the networks are exactly identical, right? That the parameters, weights, everything is identical, right? So that's what we did is we will use only one model and feed it with 2 images in the succession. So if you see the last 3 lines of the code, right? So there you will see that one image is passed through the network, right? And the second image also passed to the network separately, right? In the 2 lines. And after that, we calculate the loss value using both the images, and then we backpropagate, right? And this saves a lot of memory and also computational efficiency, because it will just introduce redundancy if we just create a exactly same network again. Then we define the contrapositive loss, right? That we just explained in the previous slides. And then it is a traditional training process, right? For any deep learning network that we do, right? Same thing we are doing for CMS network. So we initialize the network, then the loss function, and we optimize, and then we pass the first image and the second image subsequently through the network. Then we calculate the loss between them, and then we backpropagate the loss to calculate the gradient of our model, and then we update the weights, right? And eventually we save the model, but here we use the validation loss to select the best model, right? So that's how that's what the criteria to. I mean, subsequently we select the best model and replace the previous ones, right? So that's how we do. If you go to the GitLab, GitHub, so you will see that it is ran for 20 epochs, right? And you can see the entire code, and you can actually just clone the repository and you can run it yourself. So now for the unseen data pair, right? So we'll get some dissimilarity score. Now we have to decide, right, which threshold to choose, right, to qualify a pair of signatures as dissimilar, similar or dissimilar, right, or genuine or forced, right? Now here are the results that you are seeing, right? So this particular result is for the test data set, right? I mean, which has nothing to do with the training nor with the validation, right? And we were just, checking that which threshold values are making sense, right? And you can see that the threshold values I have started from 0.05, and we I just kept on increasing till 0.9, 1, and then we printed out what is the accuracy that we are getting, right? So, and if you see that, around 0.8, we were getting around 97% accuracy, right? And this is achieved by training a model on 3 people's signature, right? Validating on another 3 people, right? And finally testing on completely different set of 3 people, right? And that's what the result we're getting, and only for such small scale itself, right? Now let's see some predictions, right? So and you can see the dissimilarity score is less than if the score is less than 0.8, then the actual will be 0 right there, right? And otherwise it is forced, right? So it is actually detecting it pretty well, right? So in the GitHub, if you go, the model also I actually uploaded, right? It has around 130 MB size, so you can just copy, clone the notebook, just get the model, download it from there, and you can just do only the prediction. You don't have to even do the training, right? And you can see, right? You can probably try with your own signature as well, right? Now let's talk about the advantages of the CMS network, right? So it is more robust to class imbalance, right? So with the aid of few shot or one-shot learning, right? Given a few images per class, it is sufficient for a CMS network to recognize those images in the future, right? So that's what we just demonstrated. Only 3 people. That's what we did. Now, and it is nice to ensemble with the best classifier, and as the learning mechanism is somewhat different from classification, right? So simple averaging of it with a classifier can do much better than averaging to equally, very likely correlated supervised models, for example, gradient boosting or AdaBoost, etc. And it can learn from semantic similarity also, right? So CMS focuses on this learning embeddings, right? Because as we saw it was like 128 feature space embedding that we have got at the end of it, right? And then we calculated the dissimilarity score. So it plays the same classes or concepts close together, and hence it can learn the semantic similarity also, right? And obviously, every technique has its own disadvantages. Now, as CMS network involves quadratic pairs, right? As while creating the training data set itself, right? To learn, and that's why it is slower than the normal classification type of learning, which is point-wise learning, right? Because there, one example is one image, right? Here, one example is a pair, right? So that's how it is, right? Now, it doesn't actually output the probabilities, right? So, since the training involves pairwise learning and we use the counterpositive loss, so we don't get the output probabilities of the prediction, right? But instead of that, we get the distance between the pairs, right? So that's all about it. So these are the reference, and the data set that has been used is open source data. The code you will find here, the SIGNet paper that has been implemented, you can find in the link, right? Other useful reads, you can actually go through these links also, right? All right, so we actually reached the end of the presentation. So let's come back to the Q&A. We have just 2 minutes left. So let me see where I leave. So link to the PPT, I'll push it to the GitHub. And before that, let me share the GitHub link also, right? So Mm, yeah, so I got it. I'm pasting it here. So here is the GitHub link. You can you can actually go there. Just I mean, keep track of that link. I'll upload this presentation also in half an hour. So any pre-training will improve. Uh, so pre-training is going to okay. So this is a findings that I have seen, right? So this data set, right, has two types of data, right? One is the Bengali signatures and the Hindi signatures, right? What I did is I took disjoint set of users, but I did not change the language, right, for that. What I saw, if I train the model on Bengali images, right, and use that model to check the authenticity of a signature which comes from a Hindi script, right, then I saw not so good results there, right? So if we change the language, right, it is not actually giving so better result if we do it in the same language, right? So we I mean pre-training model. I hope it is going to help, but I think we have to try it out and see, right? But for this particular exercise, that what I've done, I saw that if we change the language, then it is not actually working pretty well, right? Now, pre-training model can be used in two aspects, right? One is just doing the transfer learning while training the model itself, or we can actually use during the prediction part itself. That is, we train on a different languages and predict in a different language signature, right? So those are the things that we have to actually check it out. But the example that I gave for this particular data set, that is training the model on Bengali images and predicting on the Hindi images, right? So then it is not actually was giving around 70% accuracy, not so good, right? All right, so I think we just reached the end of this time. So what you can do is you can actually go to my LinkedIn or Twitter, or you can go to my website and you can actually contact me, and I'll definitely revert back with probably some ad hoc meetings or some mail threads we can exchange, right? So thank you so much for joining this session. And these are the tough times we are going through, and hope this COVID nightmare ends soon. And stay safe, take all the precautions, and wish you all the best. Thank you so much.